Hi, my name is Mason Klein, and I'm a product taxonomist with Industrial Data Associates. And today we're going to be talking about knowledge graphs. What are they and how are they used in the marketplace? So when we talk about knowledge graphs, what I'm talking about are webs of information with defined relationship types. Knowledge graphs will use a formal ontology that standardizes information across the graph so that it can be read by an AI or machine learning algorithm. What that means is that knowledge graphs can be used to generate new information based on the existing entities and their relationships. They can be leveraged for search to help make search more relevant and accurate. They can serve as knowledge bases for AI algorithms to give them a set of data to help infer information and deduce new information off of. As well, they can be used to create new relationships, mappings between disparate data sets. So we're going to talk about all those uses in more detail, but first I want to drill down a little bit more on the definition of what a knowledge graph is. So this is one of the things that makes talking about knowledge graphs a little bit difficult, is that because different people sort of have slightly different definitions and they're using knowledge graphs in slightly different contexts. So what we're going to be talking about when we talk about knowledge graph is really that graphical representation of knowledge with different formalized relationships, as well as the ontology, which is the standardization of data across the knowledge graph, which allows you to draw meaningful information from it. The current kind of wave of information and use of knowledge graph really kind of stems to Google, which about 10 years ago announced in a blog post that they were going to be using knowledge graphs to help increase the accuracy and some of the relevance of their search results, organize the information into a more useful way. But that also created some ambiguity around knowledge graphs because they didn't really explain the model of how they're using them or give any kind of background information about what actually algorithms or ontologies they're specifically using at Google. So when we talk about defining knowledge graphs, that's sort of where the challenge appears. The phrase knowledge graph actually goes back further than Google, but in the current context, I thought this article by Erlanger and Woos, who are academics in Germany, gives a really nice definition with a little bit of a figure here to sort of illustrate their point. So they define knowledge graph as a system which acquires and integrates information onto an ontology and then applies a reasoner to derive new information or new knowledge. It's a great article here, which I've linked. I encourage people to read further into because they really explore the different sources of where this term comes from. But one of the reasons that this term also becomes a little bit difficult to define is because we can use the term knowledge graph to refer to the actual graph itself, the graphical representation of knowledge, but we can also use it to refer to the whole system. So the ontology, the machine learning algorithm, as well as the knowledge base, which they're drawing the information from. Here we can kind of see an illustration of how a knowledge graph should work. So in a knowledge graph, there are entities which are represented here as these classes, and then there are relationships, which are these semantic relationship lines that you can see between each of the entities. The relationships are directional, so we'll talk about semantics and what that means in a little bit more detail. And we'll also talk about how there are different terms around this graph which people might use to refer to the different parts of the graph. So another term for these relationships might be an edge. But the point here is that these relationships are directional between entities, and because of that directionality and that relationship type, we can deduce something meaningful from these relationships. So there's classes, there might be subclasses, there might be different types of classes, but based on the relationships between them, we can deduce something meaningful about class type 1 based on these relationships with the subclasses and class type. So I'm throwing a lot of terms at you right now, and let's look at a little bit more in detail what we mean by those terms. In the product information sphere, we're used to creating a hierarchy of product information. That's a parent-child structure which is used to organize concept, classes, categories from general to specific. A knowledge graph is organized a little bit differently, and we'll get into that a little bit more. When we use the term ontology in the knowledge graph context, what we're talking about are the controlled values, the relationship types, the concepts, the normalization rules, metadata, etc., which is applied to the domain of information. And the ontology is a really important element of the knowledge graph because that standardizes the way in which the knowledge is stored so that machines and AI algorithms can read that information. The nodes in a knowledge graph have a number of different terms that we use around them depending on the context. So for me, one of the clearest terms we can use to refer to the nodes in a knowledge graph is a concept. I like that term because it's really broad. It encompasses all of the different types of entities which can be represented as nodes in a knowledge graph, and it doesn't confine that definition because the knowledge graph is really supposed to be a flexible way of storing knowledge over any domain. Sometimes they're called classes, and the class is also a useful term because some knowledge graphs make a distinction between a class of items and an instance of a class, and we'll see a little bit of an example coming up here. Category is a term we're probably more used to seeing with the thought analog to the node or category in a hierarchy. So that's a term that you might see used as well. Vertex, however, is more of a mathematical term. So when people are building knowledge graph algorithms and they want to use a more mathematical language, they're going to use the term vertex. And a vertex is really, it refers to the point where two edges or two lines meet. And so that's a term that you might also see if you're looking at maybe more academic or mathematical writing on knowledge graphs. Now the vertexes are connected by edges, and edges is kind of, it's analog to vertex in that it's a more mathematical term and it refers to the lines in between the different nodes in a knowledge graph. You might also see this referred to as a relationship. This is my preferred language to talk about the relations between the nodes in a knowledge graph because, like concept, I think it's really descriptive of what the purpose of that line is. The relationship between the two nodes is really where the knowledge graph derives its meaning. And so that's the term that I prefer to use, and I'll be using a lot throughout this presentation. Another term you might see to refer to the relationship between nodes is the predicate. Predicate is really a semantic term. So, and we'll look at this in a little bit more detail, but semantics, just like diagramming a sentence, helps you determine the relationship between the subject and the object. So you have a subject, a predicate, and an object, and that comprises the semantic relationship, which gives meaning to the knowledge graph. And here you can see I've defined semantics as well. So I think I've just kind of covered that a little bit, but we'll take a closer look at that when we take a look at the semantic triple. The last term on here, which is semantic web, you might think of as sort of a synonym of knowledge graph, when you're specifically talking about the graphical representation. So when you use knowledge graph in a more holistic way to include the AI algorithm and the ontology, that's not the same thing as a semantic web, but the graphical representation of nodes and edges with defined relationship types, that can be thought of as a semantic web. So, in a semantic relationship, the subject and the object are connected with a predicate, and the relationship is directional. So a node, a subject can be any sort of concept, person, place, or and the same thing with an object. It could be any sort of concept, person, place, any type of noun. But the directional predicate in between is what defines the relationship between the subject and the object. This is, as I mentioned, called an edge. And an example of that would be like, the subject is a subset of the object, or the subject is a type of the object, is a member of the object. You can define that predicate in any way that you'd like, as long as it conforms with your defined ontology. But that relationship type is really how we define the relationship between the subject and the object. And this structure is called a triple. There are 3 items in the relationship, so it's referred to as a triple. And it's going to be the basis for how these knowledge graphs are coded. When you actually encode these knowledge graphs into a way that they're machine readable, it can almost be thought of as a stack of these triples. But when you actually represent that graphically, it ends up being a web. So that's why we use some of the different language around these different structures. Is really, it depends on the context in which we're talking about them.
Sorry, Mason, could you remind me what the acronym RDF stands for?
So the acronym RDF stands for Resource Description Framework, and that's it refers to the coding. We'll talk about that in a little bit more detail. Thank you for that question, though. Yeah, I kind of brushed over that, but we'll look at some of the different ways in which knowledge graphs are coded. But yeah, RDF stands for Resource Description Framework.
Great, thank you.
So ontology is another tricky term in this context. Depending on how you're talking about an ontology, if it's a philosophy class, you're going to have a different sort of spin on the meaning. They're all somewhat related, but when we're talking about an ontology within the confines of a knowledge graph, we're really talking about the formalized structure of controlled vocabularies, entities or concepts, edges or relationship types, facets and filters, the defined set of schema and metadata that is around a knowledge graph that makes it machine readable. And the ontology, what it does is it enforces this common standard for putting the knowledge into the domain, so that when a computer or an AI or a machine learning algorithm reads this information, it's able to derive the meaning that we want to assign it as well. And so it's not just a human having to interpret it, and the ontology makes it explicit so that a machine can interpret it and it can be used for analysis and reuse and common meaning across different knowledge bases. Now, when you're constructing your own knowledge graph, a lot of times it's going to make sense to reuse an existing ontology. And there are a lot out there. Depending on the domain of knowledge you're in and the use and the requirements of the knowledge graph, some of these pre-built ontologies may work great for you. You can see there are different organizations that build ontologies. Wikipedia has one, schema.org has one, the United Nations has a product ontology, GS1, which is a global nonprofit which maintains standards for data exchange, has a number of different ontologies that are available for public use, as well as academics have created different ontologies. I cite one here from the University of Toronto focused around products. and another one from a German university, which is really focused on building products. So it's a little bit more limited in its domain. But when you have a pre-built ontology, there are also drawbacks. You have generalized fields that may not be specific to your requirements. It might be a little too broad. It might not quite fit your data. So sometimes you need to build your own ontology. Building your own ontology, it has a lot of similarities to building a product information hierarchy. So you're going to be defining your domain of knowledge. You're going to be creating the classes or concepts which can go into your ontology. You're going to be adding attributes, items, instances. You're going to be defining metadata or filters or facets. You're going to be defining the relationship types. Constructing an ontology could be the subject of an hour-long presentation, probably many hour-long presentations in itself. I would like to just point out there's a really great resource from Stanford University that they publish in association with a free program called Protege, which is a graphical software that allows you to build ontologies in a graphical environment that can then be translated into one of the machine learning languages. So I would encourage you to actually check out the paper if you want to learn more about this subject, written by Noy and McGinnis. But there are 3 rules in that paper which I thought were really insightful that I just wanted to share. So the first one is that there is no correct way to model a domain. There are many alternatives available. And the best solution really depends on what are your specific requirements, what do you anticipate the future needs of this knowledge graph will be, and how does that work with your data. Someone might be able to create a totally different ontology that also meets those requirements, also anticipates the future needs, and might be totally different. So there's no one correct answer here, and that's important to remember when you're defining your own ontology. Secondly, it's an iterative process. It's impossible for a single person to anticipate all the requirements and all the needs that may arrive in the course of building a knowledge graph. And so the ontology will have to be iterated on, it will have to be updated, changed, refined as the process goes along. Thirdly, it's important to stick as close as possible to the physical or logical objects and relationships in your domain. When we're building a product taxonomy, we often think about rule number 3 as creating is-this in our hierarchy. And I think this is a similar sort of analog to that in ontology building, in that they shouldn't be very hypothetical, they should be really real to your domain. You should know what is the concept when you look at it when you're building the ontology. So those are just some good design rules, and worth exploring further if you're ever having to build an ontology. So what does a knowledge graph look like? Well, they can look a little different. This is an example here of a tools ontology, or excuse me, knowledge graph. One of the things you might notice about this is it's incomplete. Knowledge graphs are intended to be expanded as more information is added to the graph. And you can see a couple of different elements here, which I'll just point out. So you can see at the top here, we've got tool, and then below that, hand tool and power tool with the defined relationship of is a subclass of. So knowledge graphs can have hierarchy within them, but because they're a web, they are not totally hierarchical. It's just possible to define one relationship as a hierarchy. It's also important to note here that there are different colors of boxes or nodes in our knowledge graph. The dark blue represents classes or concepts, and the yellow represents instances or types. So I made a little bit of a reference to this earlier, but Some knowledge graphs create this nuance or distinction between different node types or classes in order to allow a machine learning algorithm to draw some further inferences from this information. You can see that not everything is taxonomically equal. So you have a node in here that says material. Material might be something we think of as more of an attribute within the product information space. But within a knowledge graph, all of these concepts are sort of equal on the page, and it's only the relationship which defines their differences. That allows an algorithm or a machine learning software to understand how things are related in a more complex way than just hierarchically. You can see also that the knowledge graph allows us to make connections to all over. It's a web. So nails are used with a nail gun. They're also used with a claw hammer. A claw hammer is a type of hammer, and it has a material of steel. Nails also have a material, and one of those materials that you can make nails out of is steel. So the knowledge graph is really a web, and it's made to make all the connections which could be used to drive whatever functional requirements you have. So earlier I made reference to some of the coding standards used with knowledge graphs. Having knowledge graphs in a machine readable format is really important for getting a lot of the functionality out of them. Of course, you could build one like I just showed on the previous page that's just graphical, it's just for humans to look at and think about, but where the real advantages come is when they're machine readable. So some of these coding standards allow you to do that. The first one is called OWL, which is the web ontology language. They kind of chopped and screwed those words to make the acronym more memorable. But that's the basic language which a lot of ontologies are stored in for web consumption. RDF, which we talked about briefly, the resource description framework, that's a format which contains those semantic triples or triplets of the subject, predicate, and the object. And that is the basic building block of a knowledge graph. RDFS would be a schema that's used with RDFs. So this is standardized and in a language that's used for maintaining knowledge graphs in the RDF format. The next one is Turtle. So if you wrote your knowledge graphs in RDFS, it would be really tedious because the relationships and everything between them, the different nodes or vertexes need to be really explicit. So Turtle is a terser, more succinct language that's easier to write that people can use to write knowledge graphs in. And then the acronym Turtle comes from TRTL, making it a little bit easier to pronounce as Turtle. Now, SKOS, or the Simple Knowledge Organization System, is a machine readable ontology. There are a lot of different machine readable ontologies, and programmers who work with knowledge graphs, knowledge engineers, they might have their own ontology that's machine readable, that's really specific to their domain of information. SKOS is just a common domain agnostic one that I think is important to know just for reference, but that would be an example of a machine readable ontology. The last one is Sparkle. That is a recursive acronym, so it stands for Sparkle Protocol and RDF Query Language. That is the query language which is most often used with RDF and RDFS to search, analyze, build, change knowledge graphs. We're going to talk about Sparkle in a little bit more detail, but Sparkle is actually based on Turtle. So if you can code in Turtle, you can query in Sparkle, pretty much. There's some small differences, but that's the relationship. So querying with Sparkle. As I mentioned, Sparkle is a recursive acronym, which is just kind of a weird thing, but not really that important for using it. What's important is Sparkle is not just a querying language. It doesn't just ask the knowledge graph information and get it back. It can also be used to add data, remove data, create new nodes or relationships within the knowledge graph. It uses 4 main query types. So an ask query, which is just a matching query on the knowledge graph or the semantic web. A select query, which not only matches, but adds tabulations and calculations into the query. A construct query, which creates new instances of new semantic relationships by submitting various variables and seeing how they match to the knowledge graph. And finally, there's a describe query, which matches are identified when adding new information to the knowledge graph and new relationships, and then comes back with further inferences and deductions from the semantic web. So how are these knowledge graphs used? Well, as I mentioned, Google really kind of kicked off the current interest in knowledge graphs, and Google obviously, or maybe not obviously, is using them for search. So Google uses a knowledge graph, their huge knowledge base of information and articles that they have within their data stores to make their search results more relevant and accurate. So, a typical search engine or search technology would match on different strings. It might have weighting based on previous searches and results. But what the knowledge graph does is it allows you to take a search, understand the context of the information that you're looking for, and then return results which are organized to be more useful, to help you understand a little bit more deeper the results that you're getting here. So in this example, which I've illustrated, we are searching for a Jaguar transmission. Now, based on the string, it can kind of understand the context of where it wants to get results from. It's not looking for big cats. It's not looking for football teams. It's looking for a car transmission. A Jaguar is the make. Jaguars make certain car models which have transmissions, and transmissions have different types. They've got manual transmissions and automatic transmissions. And so when it returns a result to you, it organizes that information in a way that's more useful. Do you want information on manual transmissions? Do you want information on automatic transmissions? Almost certainly you've seen this in action. If you've ever searched a movie or a television show on Google, it lists in a detailed sort of organized list. Who are the cast members? What year was it made? Who is the director? How many episodes? What are the ratings? That is the Google Knowledge Graph in action that you're seeing the results being organized for you. One last thing to note here on searching is 2 popular search technologies, Elastic and Solr, both support knowledge graphing capabilities. So both of these search technologies are able to use knowledge graph if you feed that information into the search. The second sort of major use of knowledge graphs is architecture for AI or machine learning. What happens is you have this base of knowledge mapped into a semantic web. You have this formalized ontology, which formalizes the relationship types and all the different metadata, node types, etc. we just discussed. It allows the machine learning algorithm to really utilize this information, understand the meaning of it, understand the context of it, and from that meaning, from that context, deduce new relationship, additional classes of information, all kinds of insights that can be gleaned from the information. So knowledge graphs really become a really key input for artificial intelligence and machine learning. It's also worth noting that a knowledge graph may be the output of artificial intelligence or machine learning. It might say, based on all of the information that we've analyzed, we can now say these things are related, and these are the different relationships, and this is the context in which this information exists. And that output of a knowledge graph actually becomes really important for some of the other use cases. So within the product domain, knowledge graphs might be leveraged to increase the accuracy of auto classification. So auto classification is going to take new items, new nodes, new categories, and be able to place them within the hierarchy, within the web that exists. And if you also lay over AI and some of the formalized ontology concepts, that can help make this a speedier, more accurate, and quick running process. Because knowledge graphs really use relationships, that means that when you're serving up product recommendations, they're a really key technology. So you're buying a drill press. Well, based on the knowledge graph, we know the drill press has certain parts, has certain accessories, maybe a part of a bundle, may be, have certain consumables, in this case, a drill bit. It may also be used to say, oh, you're buying the drill press 4500. Well, this is a similar drill press by another maker, or this is an upgrade. This is a lower quality one. By having all those relationships explicitly mapped out, it can really serve up some of these marketing, cross-sell, upsell, recommendation functions as well. Next would be like a configure price quote engine. So when you're purchasing a complex product that has multiple optional upgrades or different parts bundles, having these relationships explicitly mapped in a knowledge graph can help make this technology run. So do you want this laptop with a processor upgrade? Well, that means it requires more power, so you also have to have a battery upgrade. These explicit relationships, which are mapped within the knowledge graph web, really allows these engines to serve up all the parts, all the options in a really intelligent way. Next, another really major use for knowledge graphs is integrating disparate knowledge bases. So when you have a common ontology in a machine learning algorithm, it can ingest these knowledge bases and identify the links between them. So a major, example of this would be like if you have, or on the screen, I should say, an example of this is like you have home HVAC with certain types. You've got ducted home HVAC, you've got ductless, you've got radiators, you've got heat, you've got AC. These things are analog to the commercial units, which have similar functions, but they're really different machines. They're different machines, different parts, different market segments. But what a knowledge graph can do is it can say, these things are analog, and we're going to create the mappings between them based on what we know from our AI algorithm, our knowledge bases, and our formalized ontology. So you might think, well, this sounds very similar to a product taxonomy. How are these different? Well, they're different in a number of really key ways. So a product taxonomy is a hierarchy. When you're navigating a website looking for a product, you move from the general to the specific. Knowledge graphs are hierarchical, so they don't move from general to specific. They only contain concepts and semantic relationships. The different concepts don't have to be taxonomically similar. They can be taxonomically totally different, but there's a relationship between them, so they can be on the knowledge graph together. Knowledge graphs can use a product taxonomy. So product taxonomies have sometimes explicitly defined relationships based on the hierarchy. They can have attributes, they can have values and concepts. These can be really key inputs into defining a formal ontology. This is where you can derive your controlled vocabularies and relationship types from, but there are different structures with different purposes. Another difference would be that product data lives at the terminal level of a taxonomy. Product data can live at any point in the knowledge graph. So that makes the knowledge graph maybe less useful for managing product data and more useful for ingesting and analyzing product data. So there's really no distinction between the different classes in the knowledge graph, except for those directional semantic distinctions which connect the different nodes. As I mentioned, knowledge taxonomies can be a key input into a knowledge graph. They have these hierarchical relationships and associations which can be harvested. Taxonomy, you're often building governance documents when you're building a taxonomy. Those can be reutilized in creating a formalized ontology. You're going to have your preferred terms, your non-preferred terms, your relationship types in those governance documents. Those are all really key inputs into creating an ontology for a knowledge graph. But the knowledge graph is going to use the AI. It's going to use the machine learning algorithm to derive information, to infer new information, and it's going to have a different set of requirements and a different set of governance documents around it. One last thing before we conclude here is just to look at some of how knowledge graphs are being used for personalization. So Google and others have written a number of white papers on this topic. Because these knowledge graphs are domain agnostic, that means they can be applied to personalized information. So if you have a base of information about a specific person, maybe their social media, their browsing history, what they've looked at previously on your website, what they've purchased previously, and you can identify that's the user that's accessing the knowledge graph, you can leverage those past interactions with the data to create relationships, to infer what they might need, what they might be looking for. Did they buy a drill press previously? Well, maybe they need parts for it now. So there are a lot of applications for personalization in knowledge graphs, but it really just depends on, have you identified the user which is accessing this information? Do you have a knowledge base about that user, which you can then leverage with AI to feed them personalized results or personalized information? A company like Google, which has an enormous base of information, you use Gmail, you use GChat, you buy things from their shopping services, they can get a little bit closer to some of this personalization. Or if you're a major e-commerce enterprise with authenticated login, and you know what these users have done previously, you can really use that to feed them back services or products that they might want. But again, that just kind of depend on the situation and sort of the domain in which the knowledge graph is being used. So there are a lot of really great resources online. I know that was a lot of information pretty quickly on knowledge graphs, but there's a lot of information online. There's a lot of different perspectives, ideas. There are freely available AI algorithms which can be applied to different knowledge bases. There are primers, there are ontology builders. Here are some really great resources I would definitely recommend checking out if you're interested in this topic further. I linked to the original Google blog post, which kind of kicked off the interest or the contemporary interest in knowledge graphs. You can look up documentation on the different coding language. You can access different knowledge bases. So DBpedia and Wikidata are basically semantic webs that can be utilized by different users to sort of do research and create AI experiences. There are good primers from IBM and the Turing Institute and Stanford that are worth checking out. So if you're interested in this topic, there are a lot of really great resources available. Okay, that is my presentation on knowledge graphs. I hope you learned something.